The second to last page of your lab is titled Day 3, Error Calculation and Sources. This is the last thing that we have to go over for the lab to be complete and to prepare you for that quiz next time as well. As you just saw in what we worked on in class today, when we looked at our periodic table, a known thing can have a known density at a certain temperature. What we did in the lab was we tried to solve for the density of different things. What we're going to do with the last portion of our lab is we are going to figure out how close were we to the known value. And that's something called relative error. What I would suggest you doing right now is on the top of your lab sheet on that page is to write down the calculation I'm about to show you. And then you can use that calculation for all the parts underneath. Relative error is usually expressed as a percent, or sometimes it's even called percent error. So this will equal. So again, we can just write this on the very top of our lab on that page. The known value. Remember, our periodic table has known value. Quite frankly, at the bottom of your page has some known values of the blocks that you might have worked with. You're going to subtract the experimental value. Experimental is what we actually solved for. And we'll do an example together as a class here in a minute as well. So what did we find that the density was? It might be a good idea to keep this in parentheses because some people, when they do this calculation, are going to get order of operations throwing them off. Because the next step is we're going to divide that all by the known value. It's pretty common that this gives us a negative value. I prefer we not actually express it as a negative value, which is why I'm going to put absolute value brackets on it. When you do this calculation, it will give you a decimal value. We multiply by 100, so we can express it as a percentage. So this is the calculation for error that we have to be aware of. What I'd like us to do right now is the very first problem underneath there, where it says determine the relative error for zinc. Okay, I'm going to extend the page here. In order to solve for the relative error of zinc, we need to first know the known value for the density of zinc. So someone at the periodic table, what is the known value for the density of zinc? 7.14. Now, this is where everybody's going to be different. Well, actually, Grace and Stella are probably going to be the same because I assume that you two are partners. Go back 2 pages to where it says Day 2 density of solids and find your density value for zinc. So for example, Abby has 7.28 was her experimental value. She would then, again, make sure to subtract that, divide by 7.14, keep it a positive value, and multiply by 100. Abby doesn't have a calculator on her, so I will help her out. 7.14 minus 7.28 equals, divided by 7.14 equals, times 100 to express it as a percent. I'm actually not too concerned of how we round off this. I'm just going to go 2.0%. I'm going to go to the tenths place. Abby being 2% off the known value means she did a really good job. Her data looks good. General rule of thumb. Most people are not going to get 0% error when they do a lab. Usually they're making up their numbers if that's the case. Anything under 10% means our numbers are good. It's expected to have some issues here or there, but under 10% is good. We'll even say in chemistry class, 15% or less is acceptable. That leads us into the last thing that I need to go over before we're done. Is, okay, I can solve for error. I can solve for how far was I off. What does that mean? Why was I off to begin with? And that's what I'm referring to as sources of error. When I ask students, hey, you were above 15% error, that's not good. You should have a reason why you were off by that much. If you're off by 25%, what's going on here? The number one answer students give me is human error, which is the dumbest thing I could possibly hear. Human error is you saying, I did something wrong. You know what should have happened then, Avery? You should have done it right. So people will say, you know, I was 25% off because I did my calculation wrong. Well, then do it right. I was 25% off because I misread the scale. How do you misread a digital scale? I was 25% off because I don't know how to read a graduated cylinder correctly. Well, that's what we're trying to see if you know how to do and we're assessing. You saying human error is you on a quiz saying, I don't know the answer to this, but I'm being honest, so give me credit for that, huh? There's no points for honesty in here, Stella. We're either right or we're wrong. If anything is a mistake that you made, that is not an acceptable source of error, because you should be doing things correctly. However, the last thing I wrote down on the smartboard is there are things that are out of your control. Let's flip to the last page of the lab. And that's what the last page is going to try to explain here and have you also talk about. If I look at number 1, it says both steel and air are mixtures, so they're not pure. I'm going to stop right there. If you are not pure, how do we know what your density is? When we had you do the density of water, we used distilled water. That came from this jug. It's H2O and nothing else. If I would have had you use tap water instead, tap water has things mixed with it. And because of that, it's not pure. A known value only exists for things that are pure. If it's not pure, who knows what it is? And that's what number 1's addressing. Number 2 says if a sample is not pure, this will affect the known value of the density. You have no control over impurities. Back to the smartboard. Things that are out of your control, okay, I can accept that. That there are some things that you can't control, and the purity might be one of them. What I can tell you right now when you answer that number 2 is when you do your error calculations on the previous page, there's going to be one thing that you are going to have like an 80% error for, and it's not your fault. I actually had some of the gentlemen in the back of the room mention something to me about that before. They looked up the density of an element. They're like, wait a minute, that doesn't make sense based upon what we saw in the lab. And when they said that, I was so happy that we are putting 2 and 2 together. Too often students do the math and they don't think for a second of what does that actually mean. So some things aren't your fault. The other way that we can use error calculations is question number 3 at the bottom of the lab. It says, which of your samples gave you the best results? So in other words, when you're done calculating error on the previous page, one of them, and heck, for Abby, it might be the zinc. 2.0% error is really good data. We should be able to explain why our results were really good. Sometimes it's a matter of what equipment were we using. If we have equipment that can give us more levels of estimation, we should get better results. However, not everything could fit in a tiny graduated cylinder that has markings to the 10th place. Some equipment doesn't give us as many digits. We're probably not going to get good results if we can't get as many digits as what we'd hope for. When we talk about sources of error, what we have to keep in mind is, 1, if it's something that you made a mistake with, that can't be acceptable. If it's something that's out of your control, well, maybe this is something that could actually give us poor results. The number 1 issue is actually mentioned in this lab report of purity. If we don't have pure substances,